So now we will discuss one more simple topic in our electrostatics, that this topic is very much useful when we have no vectors. That how to identify the electric field intensity or how to obtain the electric field intensity without taking any vector. That we have a scalar quantity, some scalar quantity, but we require a vector electric field intensity. That this is possible with this particular one called as electric potential. So how the electric potential is defined? So this electric potential is defined with V, that's denoted with V, and how it is defined? Already we know it's the potential energy in our physics, that say this is also related to that one only, that simply it is defined as the total work done to move a charge in presence of electric field from one location to another location. So for some time just you remember this one as electric potential, but this is not exactly electric potential, later we will observe what it is. So till that just you observe this one as electric potential, right? How it is defined once again? It's clearly it is the total work done per charge to move a particular charge in presence of electric field from one location to the another location. So here what we have, some electric field intensity. So let us take, this is the electric field intensity what we have. So in presence of that electric field intensity we have a charge, that we placed one charge. Let us take some charge Q was placed here. We are trying to move that particular charge from one location to another location along a path. So let us take, this is the path what we are considering. So along this path this charge was moved, right? Now let us take the initial position of this path is A, the final position of the path is B. So definitely some work done will be there. That the work done per this charge will give us the potential. So simply as per the definition, V is equals to, as our notation is V, I am writing V here, V is equals to the total work done per charge. So if you take the work done and divide that one with the charge, obviously what we get is some quantity, right? Now how the work done can be calculated? So the work done can be calculated using the force which is applied on the charge and how it was moved. There is nothing but the force into displacement, that already we know. So the work done is equals to simply force into displacement L. But here clearly observe the length what we are considering, the displacement what we are considering is not the exact perfect shape. For that what I do is I will try to take a differential length dl, a differential element dl. Because of for that particular differential length dl, how much work done will be there? I will take that one as differential work done dw. So simply dw, differential work done, is equals to the force acting on that one because of the differential length dl. Since the force and dl, so both are vectors, don't take the normal multiplication, we are supposed to take a dot product between them. And here what I assume is the work done was done by the external agent. So the work was done by the external agent, that's why I will place a negative sign before this equation. That is, here clearly I am observing the differential work done because of the differential elements, for this differential element to move a particular charge from this point to this point. That's a very first small location, right? So dw is equals to minus f dl. That is the equation what we have. Now if you modify this equation, so by replacing this f with q into E, so already we know the electric field intensity is equals to force per charge. So which is nothing but minus q E dot dl. We can replace that since E is the vector quantity, a dot product is applicable here, right? Now what we want is the total work done. The total work done is nothing but the integration of this particular quantity. So integral minus q E dot dl. Q is a charge what we have, and this is clearly this is a scalar quantity and it is uniformly distributed, it's independent of space or any other. So clearly bring it out. Then this can be written as minus q, so integral E dl. Now what is this integral? This integration is for calculation of the total work done to move this charge from point A to point B. So along the line, that is from A to B, we are supposed to integrate this one. So the work done is from integral A to B. Here also this is integral A to B. E dot dl. Now as per our definition of the potential, it's the work done per charge. So work done is here, charge is on the right hand side, bring it to the left hand side. So work done per charge, which is nothing but minus A to B E dot dl. This is nothing but potential with that what we defined. So here clearly the potential V is nothing but the total electric field intensity multiplied with the distance as where the charge was travelled. That is from point A to point B. Nothing more than that. It's a very simple one. Now what are the units of this potential? From the basic definition, what are the units of work done? Joule. And what are the units of charge? Coulomb. So the potential can be represented as joule per coulomb. Or so one more, Newton meter. So work done is nothing but force into displacement. Force Newton, displacement is meter. That is Newton meter per coulomb. But wait for some time, so they are not the units what we use in our real time. So the units what we use are volts. So as per the name volt, as a scientist name, so the units are given as volt. But these two, so what we discussed are also right, that we can use them, no problem. That is joule per coulomb, Newton meter per coulomb, are the mostly useful unit is volt. So simply V is equals to minus integral A to B E dot dl. This is the equation what we use, and this is very important equation which gives many relations. So right now we will discuss as a particularly about this particular relation only. Right now, just now we obtained the relation between V and E as V is equals to minus, it's a line integral, that's from point A to B E dl. That's what we have. Now replace this equation of E here. So if you replace the equation of E here, so minus integral Q by 4 pi epsilon naught R square AR, and let us assume the line is also in the same direction of R, that is dl AR, that is in the direction of R, that what I take is dr AR. So now, so if you take the dot product between them, that's what we get is 1. So minus integral Q by 4 pi epsilon naught R square in the direction of AR, it's multiplied with dr AR, it's just what we get is dr. Now, so from which point to which point we need to integrate this one? From point A to point B. So point A to point B means we are supposed to take the distance vectors, the position vectors of our point A and point B. Let us take the position vector of point A is RA and the position vector of point B is RB. So the integration is from RA to RB. So clearly after integrating this one, what we get is just, it's a very simple integration, that's what we have is a 1 by R square dr, and what we get is 1 by 4 pi epsilon naught RB minus Q by 4 pi epsilon naught RA. That what we have defined. So V is equals to, that is nothing but the electric potential is equals to Q by 4 pi epsilon naught RB minus Q by 4 pi epsilon naught RA. And if you observe them, it is not a simple quantity, it is a difference of two quantities. That something was subtracted from another thing. What it is called? So it is called the difference of absolute potentials. That's why always we are supposed to say this V as potential difference. We are not supposed to say that V as potential. That is not potential, this is a potential difference. So whenever we are calculating V, so that is not a simple potential. Once again remember that. It's a potential difference between 2 points. That here, as we discussed, somewhere at point A the charge is there, it was moved up to point B in some path, and we are calculating the potential difference between these 2 points, right? So what is this quantity now? If this the entire thing is a potential difference, now what is this quantity and what is this quantity? So this quantity is called as the absolute potential at point B, and this quantity is called as the absolute potential at point A. Now what is that absolute potential again? So as we said, there will be no potential, only potential difference will be there. So what is this absolute potential? Once again, this absolute potential is the potential difference between this particular point to the another point where the potential is 0. So clearly VB, that what I say is the absolute potential. This absolute potential is the potential difference at this particular point to the another point where the potential is 0. In the same way, VA can be written as VA minus 0. So everywhere what we are supposed to do is we are supposed to take the potential difference only. That the potential difference is nothing but the difference between, or the potential difference between 2 points. Here if you are considering the absolute potential is the potential difference between that particular point to the, it's a potential, we are considering another point where the potential is simply 0. So here what I do is I'll try to change this notation as VAB. So VAB is equals to this Q by 4 pi epsilon naught RB minus Q by 4 pi epsilon naught RA. As we set this one as the absolute potential VB and this one as absolute potential VA, simply VAB can be written as VAB is equals to VB minus VA. So it's a very simple relation that what we have for the calculation of a potential difference between 2 points. And clearly observe this potential difference is a scalar quantity. It is not at all a vector quantity. So see also sometimes it may be called as scalar potential, scalar electric potential. Scalar electric potential is nothing but Q by 4 pi epsilon naught RB. Right? Now using this scalar potential we can obtain the electric field intensity. We have this relation. So from this relation with little modification we can get the electric field intensity also. So we require the relation between that scalar potential and electric field intensity now. Now to relate our electric field intensity with the electric potential, so once again consider the basic equation. V is equals to minus line integral of E dl. That's what we have. Now what I do is I'll differentiate on both sides. So that is dV is equals to, so minus E dl. That's what we have. For our convenience, I'll try to rewrite this differential quantity in its equivalent in rectangular or Cartesian coordinate system, and I'll try to write this E in Cartesian coordinate system, dl in also Cartesian coordinate system. So how to write down the equivalent of this differential quantity using the differential calculus? This dV can be written as dou V by dou x dx plus dou V by dou y dy plus dou V by dou z dz. That's the equivalent of this dV in rectangular coordinate system, which must be equals to minus that E can be expanded in rectangular coordinate system with its components Ex, Ey, Az. That is Ex, Ax plus Ey, Ay plus Ez, Az dot TL. The differential length equation in our rectangular coordinate system is dx Ax plus dy Ay plus dz Az. So just what I did is I wrote the equivalent of all the components what we have here, nothing more than that. So which is equals to, if you take the dot product, so minus Ex dx plus Ey dy plus Ez dz. This is the right hand side what we have after considering the dot product between Ax, Ay, Az and Az. Now compare the right hand side term with the left hand side term. So here we have dx, here also we have dx, dy, dz, dz. So if you compare them, what we get is Ex is equals to, so minus dou V by dou x. Next in the same way, Ey is equals to minus dou V by dou y. Ez is equals to minus dou V by dou z. So this is the comparison that what we took. Now replace this Ex, Ey and Ez in our absolute electric field intensity equation. So in the electric field intensity equation, instead of Ex we can write down as a minus dou V by dou x. Instead of Ey, minus dou V by dou y. Instead of Ez, minus dou V by dou y. So the electric field intensity equation now can be written as E is equals to minus of, right, this minus I took common, dou V by dou x Ax plus dou V by dou y Ay plus dou V by dou z Az. So the entire minus I took common here. So E is equals to Ex Ax plus Ey Ay plus Ez Az. Now just observe here, this V is a scalar quantity, it's not a vector quantity. So dou by dou x Ax on a scalar, dou by dou y Ay on a scalar, dou by dou z Az on a scalar, right? So clearly this represents the gradient of that particular scalar. So this can be written as minus gradient of V, that is minus del V. Simply this is the relation between our electric field intensity E and our electric potential. It's a potential difference V. So E is equals to minus gradient of V. So this E is equals to minus gradient of V is a very useful equation that gives the electric field intensity when we have potential. So till now in our Coulomb's law and Gauss's law, we obtained the electric field intensity in different ways using the vectors. But whenever there is no vector, or so whenever the vector is not available or no vector quantity is available, then how to obtain the electric field intensity? Simply take the potential. So the electric potential can be applied with the gradient that we are supposed to observe in which direction it is taking the maximum rate of change. Then the electric field intensity can be easily calculated. So E is equals to minus gradient of V is the relation between our E and V. Now we will try to obtain a peculiar relation. That's how this E is related and how we can interpret this E for static fields. For that what I do is I will try to examine what is the potential difference for a closed loop. Let us take, this is the path what we are considering from point A to B, and this is the path what I will consider from B to A. So I want the total potential for this particular closed loop. Now observe, VAB initially I am calculating, VBA at the next I am calculating, the total potential is nothing but VAB plus VBA, that is VAB plus VBA, which is equals to, so directly by seeing itself you can say that it is 0, right? VAB is VB minus VA plus VA minus VB. So VB minus VA plus VA minus VB is equals to simply 0. So the total potential difference from this point to this point, nothing more than that. For the total potential from point A to point A is always 0. Now what is the equivalent of this one? Minus, here what we are doing is we are taking the closed line integral. The closed line integral of E dl, which is equals to 0. Now what I do is I will try to apply Stokes theorem here. Since we have closed line integral, we can apply Stokes theorem. So this which is equals to surface integral of, since this particular closed line will forms a surface, say surface integral of del cross E ds is equals to 0. Now clearly examine here, for any arbitrary surface what we are considering, this surface is the existing one, arbitrary one. So clearly this del cross E must be equals to 0, the integrand must be equals to 0, that del cross E is equals to 0. This is the equation which is very much useful for us to understand the electrostatics, a static charge. So what you can interpret this equation, how you can interpret this equation? Del cross curl of electric field intensity is 0. Curl of electric field intensity is 0 is nothing but the electric field intensity has no rotational nature. So whenever the charge is static, till now we discussed about the static charges only. Whenever the particular charge is static, the electric field intensity has no rotational nature. So this is one of the important equations we need to remember, and called as Maxwell's equation for static fields. This del cross E is equals to 0 is Maxwell's equations for static fields in its point form or differential form, and this equation what we have, that is line integral of E dl is equals to 0, is also called as a Maxwell's equation in integral form. So whenever we have a closed loop path, clearly the potential is equals to 0 gives us this beautiful relation, that del cross E is equals to 0. Now we will examine whether it is possible or not with the help of our potential. Already we derived one equation, that is the relation between our E and V, that is E is equals to minus gradient of V. Substitute is the minus gradient of V here, that is curl of minus gradient of V. What will be the result? Already we know curl of gradient of any scalar is always equals to 0, that what we got here. So clearly for static fields, this del cross E is equals to 0 is the most important equation that must be satisfied. Otherwise we are not supposed to say that it is a static field. For time varying fields we have another relation, later we will discuss that. But clearly remember, for static fields If it is not satisfying, this del cross E is equals to 0. It is not at all a static field, and it is not at all a valid electric field intensity what we have. So now from this one, what I try to do is, I will try to give you one more unit for this. So what is this? Minus gradient of V, dou by dou x of V, dou by dou y of V, dou by dou z of V, right? So what I do is, just I will write this one as the potential divided by dou by dou x, x is distance, so that is d, minus V by d, right? So electric field intensity can be written as volt per meter. So later we discussed, so before that we discussed one more unit for this electric field intensity. What it is? Newton per coulomb, that's force per charge. But here just now what we took is volt per meter. This is the most useful unit for our electric field intensity. So we can use this Newton per coulomb also, no problem, but this volt per meter is the most expressing one, that what we use for our electric field intensity. So clearly the voltage and electric field intensity will be related with this equation, and this del cross E is equals to 0 is the most useful equation for observation of the nature of electric field intensity.